How old is the Earth? 100 years ago, nobody knew. The best educated guess from the most respected physicist of the 19th century was 20 million years. The answer we accept today is roughly 4.5 billion. The two numbers differ by a factor of more than 200. Not a correction, not a refinement, a complete restructuring of what humans believed about the age of the world they lived on. And the tool that settled it was not a telescope. It was not a better fossil. It was not a philosophical argument. It was an element that everyone else was using for bombs or for power, and that one chemist in Chicago used for something else entirely. He used it as a clock. And the clock had been running for 4.5 billion years, patient, invisible, unbothered by civilizations rising and falling above it. The clock was uranium. This is the video I have wanted to make for a long time. Uranium has a public reputation, and the reputation is almost entirely about weapons and reactors. That reputation is real. It is also a distraction. There is a deeper story about this element. And the deeper story is not about release of energy. It is about the measurement of time. Uranium is, by a significant margin, the most precise natural timekeeper that exists on Earth. It is more regular than any pendulum, any mechanical escapement, any quartz crystal. Its rate of decay was set by physics at the moment its atoms formed. And nothing that happens to a uranium atom afterward, not heat, not pressure, not chemistry, not pulverization, not mixing with other elements, changes that rate in any way that can be measured. The clock is the atom. The atom is the clock. And for the last 70 years, geologists have been reading it. Start with the atom, because the atom is where the clock lives. Uranium is element 92 on the periodic table. For a long time, it was the heaviest naturally occurring element known, though a few rarer ones have since been identified in trace amounts. An atom of uranium contains 92 protons in its nucleus, and depending on the isotope, either 142, 143, or 146 neutrons. The three natural isotopes with mass numbers 234, 235, and 238 differ only in neutron count, but those small differences in the nucleus produce enormous differences in behavior. Uranium 235 is the one that sustains a chain reaction. Uranium 238 is the one that makes the story of this video possible. And uranium 234 is a transient member of the family, present in small amounts because it is itself a product of the slow decay of its heavier relative. The heaviness matters. A uranium nucleus is, in a literal sense, too large for comfort. There are 92 positively charged protons packed into a space smaller than a 10,000th of the diameter of the atom. They repel each other with the electromagnetic force. Something has to hold them together, and that something is the strong nuclear force, which is powerful but short-ranged. Inside a small nucleus, the strong force dominates easily. Inside a very large nucleus, the strong force is straining. Every proton repels every other proton, and the electromagnetic repulsion grows with the square of the number of protons, while the strong force holding them together grows only linearly with the number of nucleons in contact. At some point, the balance tips and the nucleus becomes unstable. Uranium sits on the far side of that tipping point. Every uranium nucleus is, in some sense, living on borrowed time. It is held together, but only barely, and given enough time, it will fall apart. The falling apart has a specific pattern. A uranium 238 nucleus does not simply disintegrate in one event. It ejects an alpha particle, which is a cluster of 2 protons and 2 neutrons bound together. identical to the nucleus of a helium atom. By losing this particle, the uranium nucleus reduces its proton count from 92 to 90, and its total mass number from 238 to 234. It is no longer uranium. It is now thorium-234, a different element entirely. And thorium-234 is also unstable. It decays by a different mechanism called beta decay into protactinium-234. Protactinium decays into uranium-234. Uranium-234 decays into thorium-230, and so on, through 14 separate nuclear transformations, each one changing the identity of the atom until the chain finally reaches a nucleus that is stable and stops decaying. That stable endpoint is lead-206. 14 steps. 14 different elements pass through along the way, some for fractions of a second, some for thousands of years. Every uranium-238 atom that has ever existed, if it has not been split by a neutron in a reactor or a weapon, is walking this specific path. Start as uranium-92, end as lead-82. The journey takes, on average, billions of years, and the average is what makes the clock work. Here is the concept that makes all of this make sense, and it is the concept that most people find counterintuitive on the first encounter. Radioactive decay is not like a mechanical process. It is not like the winding down of a spring or the draining of a battery. An individual uranium atom does not decay according to any schedule. It has no internal count. It does not know how old it is. At any given instant, any individual uranium atom has a specific, unchanging probability of decaying in the next second. That probability is very, very small. For uranium-238, it is roughly 1 chance in 200 quadrillion per second. The atom could decay right now, in this microsecond, or it could persist for another 10 billion years. The probability does not change. The atom does not age. The event, when it happens, is fundamentally stochastic, a consequence of the quantum mechanical properties of the nucleus, and there is nothing in classical physics that can predict when any given atom will go. This sounds, at first hearing, like a recipe for unpredictability. It is the opposite. A single atom is unpredictable. A large number of atoms is, paradoxically, one of the most predictable systems in nature. The reason is statistical. Take a gram of uranium-238. That is roughly 2.5 sextillion atoms, the number 2 with 21 zeros after it. Each one has the same small probability of decaying per second. Some will decay now, some in an hour, some in a year, some in a billion years. The spread is enormous for any individual, but the total number of decays per second, summed across the entire sample, is almost exactly predictable. It follows a mathematical curve so regular that it defines the concept of half-life. The half-life of uranium-238 is 4.468 billion years. That number means something very specific. Start with any amount of pure uranium-238. After 4.468 billion years, exactly half of the atoms will have decayed and half will remain. After another 4.468 billion years, half of the remaining half will have decayed, leaving a quarter of the original. After another half-life, an eighth, and so on. The curve is exponential. It does not depend on how much material was there at the start. It does not depend on the temperature, the pressure, the chemical environment, or any other external factor. It depends only on the intrinsic quantum mechanical properties of the nucleus, which were set when the element first formed in a stellar event older than our Sun. Let me put that number in perspective, because it is easy to say 4.468 billion years, and difficult to feel what it means. The half-life of uranium-238 is roughly equal to the entire age of the Earth. An amount of uranium-238 that's present when our planet first formed is now, today, reduced to about half of what it once was. The other half has walked the decay chain and is now lead 206. Every planet we know of has the same story. Every rock on Earth that contained uranium when it first crystallized is, at this moment, a partially completed experiment. The experiment was set up by physics at the beginning of the solar system. The clock has been running ever since. And inside those rocks, right now, are both the original uranium atoms that have not yet decayed and the lead atoms that are the end products of those that have. The ratio between them shows exactly how long the experiment has been running. In other words, it reveals the age of the rock. This is the core idea. Grasp it, and everything that follows becomes clear. Inside every piece of uranium-bearing mineral on Earth, there is a running tally. It is written in the ratio of parent atoms to daughter atoms. Count the ratio, apply the half-life, and you get a number in years. No assumptions, no philosophical argument, no reliance on a fossil record or a stratigraphic correlation. Just a ratio of atoms, interpreted through a decay constant that is a fundamental property of the nucleus. The Earth is the laboratory. Every uranium-bearing mineral is an experimental record, and for a very long time, nobody could read the record because nobody knew that the experiment was running. Shift the frame now, from the nucleus to the history of a question. To understand why the discovery of the uranium clock was revolutionary, it helps to see how stuck the previous answer was. For most of human history, age of the Earth was a theological question. In the Christian tradition, a 17th century calculation worked from biblical genealogies and placed the creation of the world at the year 4004 before the Common Era. That number, 6,000 years in round figures, was printed in the margins of English Bibles for more than 200 years. It was not an eccentric view. It was the consensus reading across much of Europe for generations of educated readers. Other religious traditions produced different numbers, but most were of the same order of magnitude, thousands of years, not millions. The first serious challenge to the biblical timescale came not from physics, but from geology. In the late 18th century, Scottish geologists walking along the eastern coast of their country noticed something that did not fit. At a place called Sicker Point, sedimentary rocks lay at sharply different angles on top of each other. The lower layers were standing nearly vertical. The upper layers ran roughly horizontal. The only way this geometry could have formed was if the lower rocks had been deposited as flat sediments under an ancient sea, then slowly lifted and tilted by forces of mountain building, then eroded at the surface by wind and water, and then submerged again under a new sea that deposited new sediments on top. 3 processes, each operating at rates that could be observed in the present, each adding up to a timescale that the geologists of the Enlightenment began to call deep time. By the early 19th century, a generation of Scottish and English geologists had concluded, based on rates of sedimentation and erosion, that the Earth was at least hundreds of millions of years old, and possibly much more. Then physics arrived with a different verdict. William Thomson, later Lord Kelvin, was the preeminent physicist of his era. He had revolutionized thermodynamics, formulated the second law with clarity that still governs engineering today, and established the absolute temperature scale that bears his name. In the 1860s and 70s, Kelvin turned his attention to the age of the Earth, and he came to a conclusion that contradicted the geologists directly. He treated the Earth as a molten sphere that had been cooling ever since its formation, radiating heat into space. Using the rate of heat flow measured through the crust and the thermal conductivity of rock, he calculated how long the Earth must have been cooling to reach its present temperature profile. His answer, after several decades of refinement, settled somewhere between 20 and 40 million years. He later narrowed his estimate further to approximately 20 million. The geologists protested. The evolutionary biologists, whose theory of natural selection required vast stretches of time, protested even more vigorously. Charles Darwin, in particular, was tormented by Kelvin's number, because his theory needed hundreds of millions of years for gradual variation to produce the diversity of life. And Kelvin was telling him he did not have it. Kelvin was not wrong about thermodynamics. Kelvin was wrong about the Earth, because the Earth had a heat source he did not know about. His calculation assumed that the planet was a closed system, radiating away its original heat and receiving nothing new. But inside the crust, at that very moment, something was happening that Kelvin could not have accounted for. Radioactive elements were decaying. The decay released energy. The energy heated the rock. And that heating, distributed through every continent, was keeping the Earth warmer than the cooling model predicted. Kelvin's 20 million years was an artifact of an incomplete thermodynamic picture. The missing piece was radioactivity itself. And radioactivity had been discovered in 1896 in a Parisian laboratory by a physicist named Henri Becquerel, who was studying uranium salts and noticed that they fogged photographic plates in the dark. The discovery was initially a curiosity. Becquerel, and soon after him the Curies, showed that uranium spontaneously emitted some kind of penetrating radiation without any external energy source. It did not need to be heated, illuminated, or agitated. It emitted continuously. Wherever there was uranium, there was radiation. The Curies discovered that other elements, including thorium and the newly isolated polonium and radium, behaved the same way. Something inside the atoms of these elements was releasing energy, and that energy had to be coming from somewhere. For a few years, at the turn of the 20th century, radioactivity was one of the great mysteries of physics. What was the energy source? Why only certain elements? Why did the radiation not diminish over any timescale the researchers could measure? The answers came in a series of papers from a New Zealand-born physicist working first at McGill University in Montreal and later at Manchester in England. Ernest Rutherford, together with a young chemist, worked out that radioactivity was, in fact, a transmutation of elements. When uranium emitted an alpha particle, it became a different element. When that element emitted its own particle, it became yet another. The radioactive elements were undergoing a slow, spontaneous, irreversible chain of transformations, each step converting one element into the next, each step releasing energy in the form of the emitted particles. Rutherford and his collaborator also worked out the statistical nature of the decay and introduced the concept of the half-life. By 1902, they knew that each radioactive isotope had a characteristic decay rate, as reliable and as specific as a fingerprint. The implication, for anyone who thought carefully about it, was staggering. If uranium decayed at a known rate, and if the product of its decay accumulated in the rock, then the ratio of parent to daughter in any uranium-bearing mineral was a direct measurement of how long the decay had been proceeding, which meant it was a direct measurement of the age of the mineral. The uranium clock had always been running. The paper that made it readable was published in 1902. The rest of the 20th century was spent, in a real sense, learning how to read it. The first attempts were rough. In 1905, Ernest Rutherford himself gave a lecture at Yale in which he estimated the age of a piece of pitchblende, a uranium ore, by measuring the amount of helium trapped inside it. Helium, remember, is the end product of alpha decay. Every alpha particle emitted by a uranium atom is, once it captures 2 electrons, a helium atom. If the helium stays in the rock, it accumulates. Rutherford's estimate, based on rough measurements, gave an age of about 500 million years. It was an enormous increase over Kelvin's 20 million. It was also, almost certainly, an underestimate, because helium is a gas, and it leaks out of rock over geological time, meaning the measured amount represented only what had been trapped, not what had been produced. The helium method gave minimum ages. For a true clock, the method needed a daughter product that stayed put. An American chemist named Bertram Boltwood, working at Yale, made the next leap. Boltwood realized that lead, which Rutherford and others had tentatively suggested might be the stable endpoint of the uranium decay chain, was a solid, immobile, chemically stable element. Unlike helium, lead did not leak out of a rock. Once a uranium atom completed its 14-step decay and became a lead atom, that lead atom remained locked in the mineral lattice, essentially forever. Boltwood measured the ratio of uranium to lead in a number of uranium-bearing minerals, applied the estimated decay rate, and in 1907 published ages ranging from 400 million years for the youngest samples to more than 2 billion years for the oldest. The numbers were revolutionary. They were also, as would become clear later, not quite right in detail, because Boltwood did not have the precise decay constants, did not know about the different isotopes of uranium and lead, and could not rule out contamination. But the order of magnitude was correct. The Earth was billions of years old, not thousands, not millions, billions. Over the following decades, the technique improved steadily. The discovery of isotopes, first in the 1910s and 20s, changed the picture. Lead, it turned out, came in multiple stable forms. Lead-206 was the end of the uranium-238 decay chain. Lead-207 was the end of the uranium-235 decay chain. Lead-208 was the end of the thorium-232 decay chain. And Lead-204 was a primordial isotope, present in the original material from which the Earth formed, and not produced by any decay process. The 4 isotopes of lead were chemically identical, but differed in mass, and by the 1940s, the mass spectrometer had been developed to the point where those differences could be measured precisely. The mass spectrometer accelerates ions through a magnetic field, bending their paths by amounts that depend on their mass-to-charge ratio. Different isotopes separate into different trajectories. By the end of the Second World War, a good mass spectrometer could measure lead isotope ratios with a precision better than 1 part in 1,000. That precision was what the clock needed. But there was still a problem. Several problems, in fact, and they almost prevented the measurement of the Earth's age for another decade. The first problem was the mineral. Uranium is not evenly distributed in the Earth's crust. It concentrates in certain minerals and avoids others. For the uranium lead clock to work, the method needs a mineral that, at the moment of its formation, accepts uranium into its crystal lattice but rejects lead. If the mineral contains some lead at the start, there is no way to separate how much of the measured lead is original and how much is from decay. The clock becomes uncalibrated. It needs, in other words, a mineral that is born lead-free. That mineral is zircon. Zircon is zirconium silicate, crystalline mineral that forms when molten rock cools and solidifies. The crystal structure of zircon has a site that readily accepts uranium atoms because the ionic radius of uranium in its 4+ oxidation state is similar to that of zirconium. But the same crystal structure rejects lead. The ionic radius of lead is too large, and the chemical bonding is incompatible. A zircon crystal, at the moment it forms, contains uranium, but essentially no lead. From that moment forward, the uranium inside the crystal begins to decay. The lead that is produced, atom by atom, stays locked in the lattice, unable to escape, and unable to be displaced by outside lead. The crystal becomes a closed system. Every zircon crystal is a sealed laboratory, and inside it, the clock starts ticking at the moment of crystallization. Zircon is also astonishingly durable. It resists weathering, erosion, and even metamorphism. A zircon crystal that formed 3 billion years ago in a granite intrusion can be subjected to heat, pressure, and chemical alteration, can be eroded out of its original rock, transported as a grain of sand in rivers, incorporated into a new sedimentary deposit, and buried again, and still retain its uranium-lead record from the original crystallization. The clock is not reset by ordinary geological processes. It takes extreme conditions to disturb it, and when those conditions occur, they usually leave detectable signatures that the geochemist can account for. The oldest zircon crystals ever dated from a remote outcrop in the Jack Hills of Western Australia have been measured at 4.4 billion years. Which means that somewhere on the early Earth, within a few 100 million years of the planet's formation, there was already liquid water, granitic crust, and conditions cool enough for crystalline minerals to form. The zircon carried that news across 4.5 billion years. It was there the whole time. We just had to learn to ask it. The second problem, the one that almost broke the whole project, was lead contamination. To measure the lead content of a mineral to a precision of 1 part in 1,000, a laboratory cannot tolerate any contamination from outside lead. And it turns out that the 20th century was, by historical standards, a catastrophically lead-contaminated environment. Tetraethyl lead had been added to gasoline starting in the 1920s. Lead-based paints coated homes, ships, and industrial equipment. Lead solder was used in food cans, water pipes, and electrical connections. Lead was in the air, in the dust, on every surface of every laboratory, on the skin and clothing of every researcher. A scientist working on a clean sample of ancient rock could contaminate it with modern industrial lead, simply by breathing near it, by picking it up with ungloved hands, by placing it on a counter that had been touched by someone who had driven to work that morning. The background lead in the environment of a 1940s chemistry laboratory was orders of magnitude higher than the trace lead that the uranium clock was trying to measure. A young graduate student at the University of Chicago inherited this problem in the late 1940s. His name was Clair Patterson. His task, assigned more or less as a routine doctoral exercise, was to measure the age of a meteorite using the uranium-lead method. Meteorites were believed to be material left over from the formation of the solar system, chunks of rock that had never been incorporated into a planet and had been drifting in space since the birth of the sun. The age of a meteorite would give a direct estimate of the age of the solar system. And since Earth is part of the solar system, the age of a meteorite would give, at minimum, the age of the Earth. Patterson started the project in 1948. He expected it to take 2 years. It took 7. The reason was contamination. Every sample he measured gave wildly different lead ratios from run to run. The values were not consistent. He would grind a piece of meteorite in a clean agate mortar, dissolve it in clean acid, run it through the mass spectrometer, and get a number. He would repeat the procedure the next day and get a different number. The variations were not experimental noise. They were contamination, lead from the laboratory air settling onto his samples during preparation, lead from the acid bottles leaching into the solutions, lead from the glassware, from the gloves, from the floor, from the ventilation system. Patterson realized that he was not measuring the lead in the meteorite. He was measuring the lead in the laboratory. His response was to build, over the course of several years, what may have been the first genuinely clean laboratory in the world. He sealed rooms, filtered air, purified acids by multi-stage distillation, remade all of glassware, personally cleaned every surface repeatedly, excluded all external contamination he could identify. He went through reagents by the gallon and personally redistilled them, drop by drop. He tested the lead content of everything he touched. He found lead in the water supply, lead in the dust, lead in the air of his own lab before he had sealed it. Every reduction in background contamination pushed the measured lead values in his samples downward, which meant that his earlier numbers had been systematically too high. By 1953, he had reduced the background contamination by something like a factor of 10,000 compared to standard practice. He was measuring, for the first time, the actual lead content of ancient rock without the overlay of modern industrial pollution. In 1956, Patterson published a short paper containing the result. Using 5 meteorites, including iron meteorites, which contained essentially no uranium and therefore served as measurements of primordial lead composition, and stone meteorites, which contained uranium and therefore had accumulated radiogenic lead over the age of the solar system. He constructed what is now called the meteorite isochron. The isochron is a plot of different lead isotope ratios against each other. For rocks and meteorites that formed at the same time from the same reservoir of primordial lead, the points fall on a straight line. The slope of that line is a function of the age. From his 5 meteorites, Patterson calculated an age of 4.55 billion years, plus or minus 70 million. He then compared the meteorite lead composition to the average lead composition of terrestrial ocean sediments, which represents a mixing of lead from crustal rocks across the whole planet. The terrestrial lead sat precisely on the same isochron line as the meteorites, which meant that the Earth had formed at the same time as the meteorites, from the same primordial material, and had been accumulating lead from uranium decay for the same 4.5 billion years. The number has been refined slightly in the decades since, but not significantly changed. The current best estimate for the age of the Earth is 4.54 billion years, with an uncertainty of about 1%. Patterson's 1956 value was, within measurement error, the correct answer. He had measured the age of the planet, and he had done it by purifying a laboratory until it was quiet enough for the clock to be heard. Patterson's measurement was the beginning of a revolution, not the end of one. Once the principle was established, geochemists realized that uranium lead was only one of several clocks they could use. The periodic table contains other long-lived radioactive isotopes, each with its own half-life, each decaying into its own stable daughter. Potassium-40 decays to argon-40. Rubidium-87 decays to strontium-87. Samarium-147 decays to neodymium-143. Lutetium-176 decays to hafnium-176. Each system is a different clock, and each has its own advantages for different types of rock and different timescales. A geologist studying a volcanic rock, for example, might use potassium argon because volcanic minerals contain abundant potassium, and the argon daughter, being a noble gas, is completely absent in the rock at the moment of solidification, which means the clock resets cleanly each time lava cools. A geologist studying very old continental crust might use uranium lead on zircon because zircon survives the violence of mountain-building events that would reset other clocks. The uranium lead system has the additional advantage of being self-checking. Because both uranium-235 and uranium-238 decay to different isotopes of lead, both ratios can be measured in the same crystal and cross-verified. If the two clocks agree, the age is robust. If they disagree, something has disturbed the crystal, and the disagreement itself often reveals what and when. By the 1960s and 70s, the toolkit of geochronology, the science of dating rocks using radioactive decay, had become comprehensive. Nearly every significant rock formation on Earth could be dated within a few percent uncertainty. The geological timescale, which had existed since the 19th century as a relative sequence of named periods, was calibrated in absolute years. The Cambrian boundary, where the fossil record first shows abundant complex life, was dated at approximately 540 million years ago. The Jurassic, when dinosaurs dominated, at roughly 200 to 145 million. The Cretaceous-Paleogene boundary, marked by the extinction of the non-avian dinosaurs, at 66 million, with a precision sharp enough to confirm the meteor impact theory by matching the age of the impact ejecta layer across continents. The origin of the first hominins. Roughly 7 million. The emergence of anatomically modern humans, roughly 300,000. The end of the last major ice age, 11,600 years ago. The clock scales. It reads time from seconds to billions of years because different isotope systems cover different ranges. Carbon-14, with a half-life of only about 5,700 years, dates archaeological materials from the last 50,000 years with year-level precision. Uranium series dating, using shorter-lived daughters in the uranium decay chain, covers the range from roughly a few thousand to 500,000 years, which is critical for dating caves, stalagmites, and human artifacts from the Pleistocene. Potassium-argon and argon-argon cover tens of thousands to billions of years. Uranium lead covers millions to billions. Samarium-neodymium covers the oldest rocks on Earth and the oldest meteorites in the solar system. The periodic table provides, in effect, a nested set of clocks, each tuned to a different timescale. For any event that left a mineral record, somewhere on the table, there is an isotope system that can date it. Put together, they reconstruct the entire timeline of the Earth, the solar system, and, through the dating of meteorites and lunar samples, the history of the inner planets. Lunar samples brought back by the Apollo missions gave ages ranging from roughly 3 billion years for the youngest mare basalts to 4.5 billion for the oldest lunar highland rocks. The oldest lunar samples are, within uncertainty, the same age as the oldest meteorites, and the same age as the Earth. The inner solar system formed as a unit, in a relatively narrow window of time, somewhere around 4.5 billion years ago. Meteorites from different parent bodies all cluster around that age. The consistency of the dates across different isotope systems, across different rock types, across different origins within the solar system, provides one of the strongest internal consistency checks in all of Earth and planetary science. If the dates were artifacts of measurement, they would not converge this way. They converge because the clocks are reading a real event, the formation of the solar system from a collapsing cloud of gas and dust. And that event happened in a window narrow enough that multiple independent methods all report the same age. Here is a thought that is worth sitting with for a moment. The uranium atoms currently decaying inside a zircon crystal in a granite outcrop in Canada. The atoms whose decay is the tick of the clock that dates the rock did not form on Earth. They could not have. The nuclei of uranium, with their 92 protons and their straining strong force, cannot be assembled in the interior of an ordinary star. The ordinary nucleosynthesis of stellar cores can make elements up to iron, but not heavier. Heavy elements like uranium require more violent conditions, either the collisions of neutron stars or the cores of exploding supernovae, events that flood the surrounding space with free neutrons, in numbers sufficient for nuclei to capture them faster than the nuclei can decay. Those captures build up heavier and heavier isotopes, and some of the products of that cascade are the isotopes of uranium. Every uranium atom on Earth was forged in a stellar catastrophe that occurred before the solar system existed. The material was thrown out across interstellar space, mixed with gas and dust from other stellar deaths, and eventually gathered into the collapsing cloud that became our sun and our planets. The uranium in a zircon crystal in Canada today is, in a literal sense, older than the Earth itself. The clock started in a dying star, and the clock has been running without interruption since. The decay of a uranium atom is not influenced by the chemistry of its environment, by the temperature of the rock it sits in, by the crystalline lattice around it, by anything at all within the range of conditions that exist on any planet or moon in this solar system. Altering the decay rate of uranium requires conditions like those inside a neutron star, where the density of matter is so extreme that the normal quantum mechanical rules begin to shift. In a crust, a mantle, a core, a glacier, an ocean, a forest, a hand holding a piece of pitchblende, the decay rate is constant. It has been constant for 4.5 billion years. It will be constant for another 10 billion. The clock does not care what happens to the rock. The clock does not care whether the rock is on Earth, or on the moon, or in a museum, or in a laboratory, or in a star that is about to go supernova. The clock reads time. That's all it does, and by reading it, we learn when things happened. Not as stories, not as inherited traditions, not as relative sequences, but as numbers. The previous video on this channel followed an element from a tunnel in the Democratic Republic of Congo to a phone in a pocket. That story was current. It was happening while the video played. This story is different. This is about an element that has been doing its work since before the Earth had an atmosphere. The scale is not the supply chain of the present. The scale is the age of everything. And the quieter the thought gets, the larger it becomes. Consider the zircon crystal from Jack Hills in Western Australia, the one that was measured at 4.4 billion years. That crystal was already ancient when the first single-celled organisms appeared on Earth. It was ancient when the continents formed. It was ancient when the oceans filled. It has been sitting in the crust of this planet, being transported, buried, uplifted, and weathered for almost the entire history of the solar system. Inside it, a small number of uranium atoms have been patiently decaying for all that time. The ratio of uranium to lead in that crystal, when a geochemist measures it, is the accumulated record of 4.5 billion separate years. Each year, a few more atoms finish their 14-step journey from uranium to lead. The crystal did not count those atoms. The crystal did not know that it was keeping time. It was keeping time anyway. There is something in this that is worth saying directly, because it does not get said often enough. The usual discussion of uranium centers on energy, on weapons, on risk, on the decisions of states and industries. Those discussions matter. They have shaped politics, warfare, environmental catastrophe, and energy policy for the better part of a century. But none of that is the oldest or most fundamental fact about this element. The oldest fact about uranium is that it measures time. It has done so since the first uranium atoms formed in a stellar explosion, long before any human beings existed to be worried about what it could do. It will continue doing so long after the sun has consumed its hydrogen, swelled into a red giant, and collapsed into a white dwarf. The decay of uranium-238 will still be proceeding, atom by atom, on the cold, dead surface of whatever remains of the Earth. The clock does not require us. The clock does not notice us. It was running before us, and it will run after us. And for a brief moment in the middle, a small number of primates learned how to listen to it. That listening is not a small thing. It is one of the quietest and most underappreciated feats in the history of science. The age of the Earth, a question that every civilization has asked, and that no civilization before the 20th century could answer, was resolved in a single experiment by a chemist who had spent 7 years cleaning a laboratory. The method has not been superseded. Every refinement of the age of the Earth since 1956 has used the same principle, the same isotope system, the same fundamental logic, and has produced numbers that agree with Patterson's to within a percent. The experiment worked because the clock is real. The clock is real because the physics of the nucleus is constant. The nucleus is constant because the fundamental interactions of the universe, whatever they may be, do not change with time in any way that has yet been detected. There is a reframing that happens when you spend enough time with this idea. The element that public discourse treats as the most dangerous on the periodic table, the one associated with destruction and contamination and fear, is simultaneously the most reliable witness to the age of the world. Those two facts are the same fact, seen from different angles. Uranium releases energy when its nucleus falls apart, and that release is why it can sustain a chain reaction and why it can power a reactor. Uranium also releases energy in smaller packets, atom by atom, in the slow alpha decay that proceeds continuously at the rate set by its half-life, and that slow decay is what makes it a clock. Same physics, same instability of a large nucleus straining against its own electromagnetic repulsion, same fundamental mechanism. In one application, the instability is concentrated into a sudden event, a fission cascade that releases its energy in a fraction of a second. In the other application, the instability is sampled at its natural rate, one atom at a time, over billions of years, and the time itself is what we measure. The bomb and the clock are two readings of the same book. The difference is how fast you turn the pages. Most of the time, the atoms turn the pages at their own pace. 100 grams of uranium-238, sitting undisturbed in a rock, undergoes about 1,200 decay events per second. 1,200 atoms, each one finding its own moment, each one stepping onto the first rung of a 14-step path that will end, billions of years later, in a stable lead atom somewhere in the same crystal. 1,200 is, in the vocabulary of radiochemistry, a very quiet count. It is barely above background. You can detect it with a good alpha particle counter, but it would not alarm a Geiger counter in a classroom. It is the sound of time passing. It has been the same sound for 4.5 billion years. The Earth is 4.5 billion years old. We know this because we have learned to read a clock that nobody designed, that requires no power, that cannot be stopped, and that has been running longer than anything else we can measure. The clock sits inside crystals that were formed when the continents were young. It sits inside meteorites that have drifted through the solar system since before the planets formed. It sits inside a small amount of material in the core of this planet, releasing heat that drives the motion of the mantle and, indirectly, the motion of continents and the eruption of volcanoes. The warmth under your feet is, in part, the warmth of a clock running. The continents you stand on are shaped, in part, by the energy that same clock releases as it ticks. The atoms whose decay defines the rate were forged in a star that died before our star was born. You are standing, at this moment, on the cooled debris of a stellar explosion, and the debris is slowly measuring how long it has been cooling. That measurement is the history of your planet. Uranium gave us the age of the Earth. It did it by being what it is, by being heavy and unstable and patient, by decaying at exactly the rate that the laws of physics assign to it. One chemist in a clean room in Chicago found a way to read what the element had been writing all along. The rest is geology. The rest is planetary science. The rest is the timeline on which every other story this channel will tell, from the formation of the first organic molecules to the rise of empires, hangs like a thread from a fixed point. 4.5 billion years, known to a precision of 1%, written in lead and uranium, inside a crystal the size of a grain of sand, in a continent that was not yet a continent when the clock started. There is another element whose clock ran even longer than this one and reads even further back. It is the lightest and simplest element in the universe. It has been around since almost the beginning, almost 14 billion years. Uranium told us the age of the Earth. The next element told us the age of everything.